everyone, my name is Nicole Andrea Di Carmelo from BSCEA and I'm gonna report about pairwise comparisons in one-factor experiments. In a one-way ANOVA, an F-test is used to test the null hypothesis that all the treatments means are equal. If this hypothesis is rejected, we can conclude that the treatment means are not all the same. But the test does not tell us which ones are different from the rest. Sometimes an experimenter has in mind two specific treatments, I and j, and wants to study the difference mu I minus mu j. In this case, a method known as Fisher's least significant difference or LSD method is appropriate and can be used to construct confidence intervals for mu I minus mu j. To test the null hypothesis that mu I minus mu j equals 0. At other times, an experimenter may want to determine all the pairs of means that can be concluded to differ from each other. In this case, a type of procedure called a multiple comparisons method must be used. We will discuss two methods of multiple comparisons, the Bonferroni method and the Tukey-Kramer method. Fisher's least significant difference or LSD method. We begin by describing Fisher's LSD method for constructing confidence intervals. The confidence interval for the difference mu I minus mu j is centered at the difference in sample means x bar I minus x bar j. To determine how wide to make the confidence interval, it is necessary to estimate the standard deviation of x bar I minus x bar j. Let ji and jj be the sample sizes at levels I and j respectively. Since by assumption all observations are normally distributed with variance, it follows that x bar I minus x bar j is normally distributed with mean mu I and mu j, and variance open parenthesis 1 over ji plus 1 over jj close parenthesis. Variance is estimated with MSE for reasons explained previously in the discussion about confidence intervals for the treatment means. Now, the quantity open parenthesis x bar I minus x bar j close parenthesis minus open parenthesis mu I minus mu j close parenthesis over the square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis has a student's t distribution with n minus I degrees of freedom. The value n minus I is the number of degrees of freedom used in computing MSE. Fisher's least significant difference method for confidence intervals and hypothesis tests. The Fisher's least significant difference confidence interval at level 100 open parenthesis 1 minus alpha close parenthesis percent for the difference mu I minus mu j is x bar I minus x bar j plus minus t n minus I alpha over 2 square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis. To test the null hypothesis mu I minus mu j equals 0, the test statistic is x bar I minus x bar j over the square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis. If HO is true, this statistic has a student's state distribution with n minus I degrees of freedom. Specifically, if bar x bar I minus x bar j bar greater than tn minus I, comma, alpha over 2 square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis, then null hypothesis is rejected at level alpha. Example 9.9. In the world experiment discussed in section 9.1, hardness measurements were made for 5 worlds from each of 4 fluxes A, B, C, and D. The sample means hardness values were x bar A equals 253.8, x bar B equals 263.2, x bar C equals 271.0, and x bar D equals 262.0. The following output from Minitab presents the ANOVA table. One-way ANOVA ABCD. Source, factor, error, total. DF 31619, SS 743.40, 1023.60, 1767.00, MS 247.800, 63.975, F 3.87, P 0.029. S equals 7.998, R minus SQ equals 42.07%, R minus SQ or adjacent equals 31.21%. Before the experiment was performed, the carbon contents of the fluxes were measured. Flux B had the lowest carbon content, 2.67% by weight, and flux C had the highest, 5.05% by weight. The experimenter is therefore particularly interested in comparing the hardness obtained with these two fluxes. Find a 95% confidence interval for the difference in mean hardness between welds produced with flux B and those produced with flux C. Can we conclude that the two means differ? Solution. We use expression 9.32. The sample means are 271.0 for flux C and 263.2 for flux B. The preceding output gives the quantity MSE as 63.975. The sample sizes are both equal to 5. There are I equals 4 levels and N equals 20 observations in total. For a 95% confidence interval, we consult the t-table to find the value t16.025 equals 2.120. The 95% confidence interval is therefore 271.0 minus 263.2 plus minus 2.120, square root of 63.975, open parenthesis 1 over 5 plus 1 over 5, close parenthesis, or open parenthesis, negative 2.92 and 18.52, close parenthesis. To perform a test of the null hypothesis that the two treatment means are equal, we compute the value of the test statistic from the expression 9.33 and obtain 271.0 minus 263.2 over the square root of 63.975, open parenthesis 1 over 5 plus 1 over 5, close parenthesis, equals to 1.54. Consulting the t-table with n minus I equals 16 degrees of freedom, we find that P is between 2 or 0.05 equals 0.10 equals 2, 0.10 equals 0.20. Note that this is a two-tailed test. We cannot conclude that the treatment means differ. If it is desired to perform a fixed level test at level alpha equals 0.05 as an alternative to computing the p-value, the critical t-value is t16.025 is equals to 2.120. The left-hand side of the inequality, 9.34, is 271.0 minus 263.2 is equals to 7.8. The right-hand side is 2.120, square root of 63.975, open parenthesis, 1 over 5 plus 1 over 5, close parenthesis, equals to 10.72. Since 7.8 does not exceed 10.72, we do not reject null hypothesis at the 5% level. The following output from Minitab presents 95% Fisher-LSD confidence intervals for each difference between treatment means in the weld experiment. Fisher 95% individual confidence intervals, all pairwise comparisons. Simultaneous confidence level equals 81.11%. The values labeled center are the difference between pairs of treatment means. The quantities labeled lower and upper are the lower and upper bounds, respectively, of the confidence interval. Of particular note is this simultaneous confidence level of 81.11%. This indicates that although we are 95% confident that any given confidence interval contains its true difference in means, we are only 81.11% confident that all the confidence intervals contain their true differences. The Bonferroni method of multiple comparisons is a general method valid anytime that several confidence intervals or tests are considered simultaneously. The method is simple to apply. Let C be the number of pairs of differences to be compared. For example, if there are I treatments and all pairs of differences are to be compared, then C equals I, open parenthesis, I minus 1, close parenthesis, over 2. The Bonferroni method is the same as the LSD method, except that alpha is replaced with alpha over C. The Bonferroni method for simultaneous confidence intervals and hypothesis tests assume that C differences of the form mu I minus mu j are to be considered. The Bonferroni simultaneous confidence intervals at level 100 1 minus alpha percent for the C differences mu I minus mu j are x bar I minus x bar j plus minus tn minus I alpha over 2c square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis. We are 100 open parenthesis 1 minus alpha close parenthesis percent confident that the Bonferroni confidence intervals contain the true value of the difference mu I minus mu j. For all C pairs under consideration, to test C null hypothesis of the form, the test statistics are x bar minus x bar j over the square root of MSE open parenthesis 1 over ji plus 1 over jj close parenthesis. To find the p-value for each test, consult the student's t-table with n minus I degrees of freedom and multiply the p-value found there by C. Specifically, if x bar I minus x bar j greater than tn minus I alpha over 2c square root of MSE 1 over ji plus 1 over jj, then the null hypothesis is rejected at level alpha. Example 9.10. For the well data discussed in example 9.9, use the Bonferroni method to determine which pairs of fluxes, if any, can be concluded at the 5% level to differ in their effect on hardness. Solution. There are I equals 4 levels with j equals 5 observations at each level for a total of n equals 20 observations in all. With 4 levels, there are total of c equals 4, 3 over 2 equals 6 pairs of means to compare. To test at the alpha equals 5% level, we compute alpha over 2c equals 0.004167. The critical t-value is t 16.004167. This value is not in the table. It is between t 16.005 equals 2.921 and t 16.001 equals 3.686. Using computer software, we calculated t 16.004167 equals 3.0083 without software. One could roughly approximate this value by interpolation. Now, MSE equals 63.975. The four sample means are as follows. Flux ABCD mean hardness A 253.8, B 263.2, C 271.0, and D 262.0. There is only one pair of sample means 271.0 and 253.8, whose difference is greater than 15.22. We therefore conclude that wells produced with flux A have different mean hardness than wells produced with flux C. None of the other differences are significant at the 5% level. Although easy to use, the Bonferroni method has the disadvantage that as the number of pairs C becomes large, the confidence intervals become very wide and the hypothesis tests have low power. The reason for this is that the Bonferroni method is a general method not specifically designed for analysis of variance or for normal populations. In many cases, C is very large. In particular, it is often desired to compare all pairs of means. In these cases, a method called the Tukey-Kramer method is superior because it is designed for multiple comparisons of means of normal populations. The Tukey-Kramer method of multiple comparisons. The Tukey-Kramer method is based on a distribution called the studentized range distribution, rather than on that student's t distribution. The studentized range distribution has two values for degrees of freedom. which for the Tukey-Kramer method are 1 and n minus 1. In comparison, the F-test uses 1 and n minus 1 degrees of freedom. The Tukey-Kramer method uses the 1 minus alpha quantile of the studentized range distribution with I and n minus I degrees of freedom. This quantity is denoted Qi n minus I alpha. The Tukey-Kramer method for simultaneous confidence intervals and hypothesis tests. The Tukey-Kramer level 100 open parenthesis 1 minus alpha close parenthesis percent simultaneous confidence intervals for all differences mu I minus mu j are x bar I minus x bar j plus minus q I n minus I alpha square root of mse over 2 open parenthesis 1 over ji plus 1 over jj close parenthesis. We are 100 open parenthesis 1 minus alpha close parenthesis percent confident that the Tukey-Kramer confidence intervals contain the true value of the difference mu I minus mu j for every I and j. To test all the null hypotheses, the test statistics are x bar I minus x bar j over the square root of mse over 2 open parenthesis 1 minus ji plus 1 over jj close parenthesis. The p-value for each test is found by consulting the student test range table with I and n minus I degrees of freedom for every pair of levels I and j for which x bar I minus x bar j greater than q I n minus I alpha square root of mse over 2 open parenthesis 1 over ji plus 1 over jj close parenthesis. The null hypothesis is rejected at level alpha. Example 9.11. For the world in table 9.1, use the Tukey-Kramer method to determine which pairs of fluxes, if any, can be concluded at the 5% level to differ in their effect on hardness. Solution. There are I equals 4 levels with j equals 5 observations at each level for a total of n equals 20 observations. In all, to test at level alpha equals 0.05, we consult the student test range table. To find Q for 16.05 equals 4.05. The value of MSE is 63.975. Therefore, QI n minus I alpha square root of MSE over j equals to 4.05 square root of 63.975 over 5 equals 14.49. The four sample means are as follows. Flux A, B, C, D. Mean hardness A 253.8, B 263.2, C 271.0, and D 262.0. There is only one pair of sample means 271.0 and 253.8 whose difference is greater than 14.49. We therefore conclude that was produced with flux A have a different mean hardness than was produced with flux C. None of the other differences are significant at the 5% level. When all possible pairs are compared, as in this example, the Tukey-Kramer method is always more powerful than the Bonferroni method. When only a few of the possible pairs are to be compared, the Bonferroni method is sometimes more powerful. Sometimes only a single test is performed, but the difference that is tested is chosen by examining the sample means and choosing two whose difference is large. When all possible pairs are compared, as in this example, the Tukey-Kramer method is always more powerful than the Bonferroni method. When only a few of the possible pairs are to be compared, the Bonferroni method is sometimes more powerful. Sometimes only a single test is performed, but the difference that is tested is chosen by examining the sample means and choosing two whose difference is large.